Legita's right there. So either see Legita in Create or send Legita an email, and she can sign you up for a research in progress stuff. We really would like to really become a community. We're really sharing ideas and building and helping each other build and make our research better. The other big difference this year is we're actually going to go, instead of from 12 to 1, we're going to go to 12 to 1:30 with the hopes of fostering more in-depth conversation. Right? So we got the feedback that there wasn't enough time for conversation, so it means we have to provide more time. What that means is when Kinsey, Becky, and Melanie are presenting today, you have to pay close attention and come up with some really good questions to really force a discussion and have us talk. So welcome once again to the first Create session of the year. There is, I just want to make one announcement. There will actually be a presentation. It's not a Create presentation, but there is a seminar next week by David Schaefer, and some of you may be really interested in his work. I believe it's on
qualitative ethnography.
Yeah, qualitative ethnography.
Or
Quantitative ethnography.
Quantitative ethnography. And is it on Wednesday morning or Tuesday morning? I can't remember.
25th.
Tuesday morning, I think, at 9:30, right? So I know David from when he looked like most of you in the room, not like Andy, but most of the other ones. When he had that kind of a complexion, I knew David quite well. He's a very creative individual, so I think you may enjoy his talk. So with that, I'm going to turn this over to Melanie and Becky and Kinsey, and thank you guys very much for kicking this off. I'm sure you're going to set a perfect tone for what, no pressure, Melanie, perfect tone for what all these research and project talks to be all about. So thank you, and welcome everybody.
All right, so I'm just going to talk for the first few slides of this presentation to kind of set the scene, and then I'm going to turn it over to Becky and Kinsey, who are going to talk more about the meat of the project that we have been doing for the past, 5 years? It's quite a long time. So you can see that there's a cast of thousands associated with this, so there's probably more people associated with the project than are here in the room right now, but and we'll talk more about that as we go along, and we have some pictures of them at the end. But just to give you a little background, just after I got here in 2013, the AAU, the Association of American Universities, put out a call for a proposed STEM education initiative. And this is a big deal because this organization, the AAU, is the major lobbying organization for many of the major R1 universities in the States and a couple in Canada. And the fact that they had turned their attention to thinking about education, it was the first time that they had, and I think that it got a lot of attention from people who are in positions to make things happen, like college presidents and provosts. And so MSU received one of the 8 grants that they gave to the 62 institutions. I think 48 of them submitted proposals. And we called it Creating a Coherent Gateway to STEM Teaching and Learning. And then just to follow up, in 2017 we got kind of a much larger scale grant to extend the work that we've been doing to a consortium of 4 universities. So MSU is the lead, then Florida International, Grand Valley, and Kansas State are also involved in the kind of proliferation of what we've been talking about. So we're now extending our Coherent Gateway, and funding came from MSF for that. And so I just want to show you what the AAU said about this. And what they wanted to do was to influence the culture of STEM departments, which is crazy, actually. And they gave these 3-year grants. They were $500,000. And if you know anything about the culture of STEM departments, you realize that this is probably not going to do the job. So, but anyway, we know that there is a fair amount of research on teaching and learning, both especially at K-12, but also in higher ed. And here's the Discipline-Based Education Research Report. Strategies are needed to effectively promote translations of finding. And so yeah, so we should do that. And how sad, this report is no longer posted on the
It uses the word evidence.
because it uses evidence. There is no Council of Advisors on Science and Technology anymore, but just a happy memory. But they did put in their report, the first 2 years of college are most critical, and we agreed. And so in our proposal, we did target the first 2 years. On our change model that we proposed, well, that we would build faculty consensus. And what we wanted to do was to develop a shared vision for the Gateway course transformations. And we chose biology, chemistry, and physics because those were the people who turned out at the meeting. And we also, there's a lesser emphasis, but also an emphasis. Obviously, we can't develop policies. We're a group of faculty. We can encourage policies that reward reform, but we did put in place a STEM teaching fellow network, which I'll talk a little bit more about in a minute. But the main thrust of our proposal was that we were going to develop a shared vision for Gateway transformation. And to do that, we didn't actually use the research from the DEVA report. We actually proposed that we would use the framework, which everybody in this room, I am sure, is completely familiar with, and base it, and we proposed that we would adapt this vision of STEM teaching and learning for college classrooms. And that's our logo. Thank you very much. Thank you, Erin. And so our shared vision revolves about discussions. So that's what we did. We actually got faculty together in discussions to build consensus as much as we could on what are the core ideas, what are the scientific practices, and what are the cross-cutting concepts. And so that was the first kind of step in this project. And the result, we hope, is three-dimensional learning. All right, so I just put this up because I think everybody in this room is familiar with this, so I'm not going to go through it in great detail, but we have published on this now. We actually have a paper in Science, it's not on there, but never mind, where we proposed that we would do this, and that has got quite a bit of uptake in the literature. And so we've got scientific practices, we've got the cross-cutting concepts, and then to round it out, what we really focused on first with the faculty was the core ideas, because if we could get the faculty to think about and understand what the core ideas of the discipline were, then we might also get more engagement in how we were going to address connecting what we teach to the core ideas. So in biology, the core ideas, were developed by biology faculty, and they look very similar, but not exactly the same as the core ideas in Vision and Change, which is the AAAS project that revolves around the same ideas. Here is chemistry, so we used different core ideas than the framework. Everything else was the same, but we had to have our own core ideas. So these are the chemistry core ideas that we have been using over the past few years. And here's physics. All right, and these were developed by discussions among the disciplinary faculty in the departments. And the STEM Teaching and Learning Fellowship, essentially we have, I'm not exactly sure, but maybe 40, 45 faculty by now have gone through this program where we talk about core ideas, cross-cutting concepts and practices, where we apply principles of backward design and evidence-centered design, because one of the things, as you'll see, is we're trying to focus on how we assess student learning. and then become part of this interdisciplinary community. And I know there are people in here who've been part of this community, and we are moving forward with that, and also now making it not only interdisciplinary, but also among the 4 participating institutions. So implementing three-dimensional learning, we believe that three-dimensional learning is going to change both how we assess students and the instruction that occurs in the college setting. So the question is, well, how are we going to assess outcomes? Because if you're familiar with any big transformation project in higher ed, typically the evidence that is proposed is not all that convincing about whether any transformation has actually occurred. So for example, the AAU actually suggested that we ask faculty, do you know about these evidence-based principles? And we actually did send that survey out, and you may have received it. But I had people come up to me and say, well, I filled out your survey, and I think I put what you wanted me to, but I don't believe it. And, so it's not very convincing evidence, right? Just because somebody knows about something or they say that they do it, doesn't mean that they do. So we decided that if we were going to do this, right, essentially it's going to lead to changes in classroom practice, and it's going to lead to changes in assessment practices. So we said that we would evaluate those changes. And so for measuring change, we could also collect the usual data, right? Persistence, grades, we could look at the affective domain, faculty perceptions. But we know that grades don't equate with learning. We know that, right? There's a lot of literature, the Deber literature, talking about how little students know. And yet students are still very successful. So that's not, we didn't believe that was all that useful, but we should do it. And as I said, what faculty say doesn't necessarily align with the practice. So we're going to be measuring change by investigating classroom practice using a new protocol that Kinsey will tell you about. And also, we're also looking at the nature of the course assessments. So these 2 protocols, the 3D LAP and the 3D LOP, are the ways that we are thinking about how we will assess change. And so that's just the intro. Now we get to the meat of the presentation. So I'll turn it over to.
It's for recording.
Yes.
See, I shouldn't have worn a dress. Or I need a dress with pockets. I didn't think about this. I think, I remember we were talking one day, when Joe was coming to these meetings, and we were talking about, well, we need an acronym. And then Joe just mentally left the room and went, for about 5 minutes. And we're just definitely one of the contributors to the early versions of this 3D Lab acronym. So thank you for that. Because now we talk about it like everybody knows it. And a lot of people do actually. Can I steal that?
Oh, sorry. I didn't mean to bring that with me. Sorry.
Okay.
You just press the go.
Okay. So, pardon me. So the 3D Lab is a protocol that essentially has 2 purposes. It helps us helps us and others so far, both characterize changes in assessments over time, but it's also been useful, and particularly here at MSU, it's been useful in the fellowship program that Melanie introduced for helping faculty think about, okay, if I have this assessment item, and here's the set of criteria that outlines, for example, how a question might reflect analyzing and interpreting data, blended with a core idea and cross-cutting concept, then why doesn't my question look like, why doesn't my question sort of meet these criteria, and what could I do to change my question to reflect it? So I think one of the best things that is in this paper is one of the supplementals that is a long list of examples, right, as we were kind of coming to coding validity, or deciding on coding validity and reliability, we were looking at, we were binning all of these different kinds of assessment questions that we could come up with and say, this isn't, and why and why not, and so forth. So there's a long supplemental that has that in there. So one of the papers that has come out that that some of the chemists put together was looking at that first purpose of helping faculty basically adapt assessment items. And this is a JChem Ed, right? It's kind of targeted at a practitioner audience. A JChem Ed paper focused on how can I look at my original task and sort of filter it through the 3D lab to make it something that might elicit some evidence of students engaging in the dimensions. So that came out just this year, this year, 2018. So for example, a traditional item might ask students to look at a reaction and calculate the enthalpy change for that reaction, so essentially the amount of heat absorbed or heat evolved from that reaction. This is very typical. Some of my favorite examples of the traditional assessment items were these kind of like, almost like rule-based, like if you have, add the number of electrons in this atom to the number of protons in this atom, and multiply it by this, and then tell me what you get out at the end. And so there's all these different kinds of skills wrapped up in a question like that. And at the end, if a student doesn't get it, you really don't know why they got it. And sometimes even if they get it right, you might not know really why they got it. So different kind of example. But this is pretty typical, and not just typical here, I think it's typical of a lot of kind of general chemistry courses, different universities. So an example adapted item, we found, it's easier to get into students' heads, right, when we can get them to construct their responses. And so a lot of times it was easier to identify or adapt items that were three-dimensional when they were constructed response. And so in some cases we ended up, sort of adapting items by taking a typical sort of selected response item and making it, a richer kind of almost activity in some cases. But not always, not always. This is one example of an example. So here, the first three subparts ask students to draw the chemical structures for these reactants and products, and then to identify in particular which bonds are broken and which are formed, right? Because sometimes students like to think, oh, I'm just going to pretend that like every bond is broken and every bond is reformed, but like that doesn't really reflect what's happening in reality. And explaining why breaking bonds requires an input of energy from the surroundings. So we could see that as constructing a model or constructing an explanation there, and using energy and bonding interactions. Then the second part D there, is asking them to do this sort of like rote mathematical work of calculating the enthalpy change, right? That's essentially all that is occurring in the prior example. And then using that calculation to construct an energy diagram for the reaction, right? So they're using that mathematics to do something. So, right, so that knowledge of that enthalpy change is actually helping them construct something that helps them understand the reaction even more. And then the last part, constructing an overall explanation for why the energy change in the reaction is either endothermic or isothermic, and what's the evidence now that they have to make that claim. So we would see this as a richer and three-dimensional example. So this would be like an example of something that we coded. I'll show you some data in a moment where we were coding lots and lots and lots of exams, and this would be an example of something that we had coded as three-dimensional, whereas the prior question we would have. So when we developed the 3D lab, one of the things that we did was just test it against exams from traditional courses and exams from reformed courses and see what we could see, right? Did we see any signal with this protocol or not? So this was an iterative process, right, of looking at exams, of refining our criteria in the protocol, looking at more questions, and also reconciling across biochem and physics. So the data that I'm going to show you today are primarily from chemistry, but it was also a process where we were, aligning ourselves between biochem and physics throughout the whole process. So each of the tables here is representing an exam. The top one is a traditional, just by question number, and the bottom one transformed. And indeed, we could see, after many rounds of discussion and like many years of discussion, actually, that we could reliably identify across the disciplines whether an item had or didn't have a sign reflected practice or cross-cutting concept or a core idea.
Hang on, Becky,
Yeah.
for a second.
Oh, I don't know how to go back. Okay. Yeah.
So the top thing was MSU courses, there were a grand total out of 20 questions, 5 that had any core idea and none had anything else.
So mostly skills, right? So one of the things that we did in the project was kind of identify, like, what are the skills that occur in, that regularly show up in a discipline, like drawing a Lewis structure, or calculating formal charge, or maybe doing a Punnett square in biology, or like drawing a free body diagram in physics, right? These are things that like are very, very, very useful tools. Sometimes you want to assess them, right? Like you don't always want to assess like this giant sort of like collection of like skills and knowledge, but sometimes you do want to do it. But they appeared to be very skill heavy, right? And not just in bio, but or not just in chem, but in bio also. Yeah. So this was, I'm going to walk you through a table here. So we ended up coding for this project. We basically collected exams. We begged, borrowed, we didn't steal, begged. We didn't actually borrow, we just begged. I begged a lot. And Melanie did too. Asking faculty if they would allow us to look at their exams. No student work here, this is just the problems themselves. We solicited their final exams, and when those either weren't appropriate for some reason, or they weren't available for some reason, or they just didn't want to give them to us, we asked for their midterm exams. So, you know, we're looking at the high stakes exams that are occurring right now in intro bio, intro chem, intro physics. So if you look at that from, we called it the beginning year, year 0. Year 0 was the year prior to the AAU project beginning, and then we continued to collect them for 3 more years after that. So it was like really, it was crazy. It was crazy. So we split them out. We have them grouped by discipline, except that we split Bio 1 and Bio 2 separately from each other. And the reason we did that is because the faculty tend to cross Bio 1 and Bio 2 not as frequently as they do in chemistry, right? So chemistry instructors tend to teach Chem 1 and Chem 2, or Chem 2 and Chem 1, or they mix around and do both. But there's much more, they're much more siloed, for lack of a better word, in Bio 1 and Bio 2. So that's why. So this is how the data are presented. So Chem 1 and 2, Physics 1 and 2, Bio 1 and Bio 2. And the point of this table is just to show you that there's sort of lots of different ways of like asking, well, what are we interested in, right? Because some instructors teach multiple sections. Sometimes multiple instructors use the same exam. And so we kind of had to get down to the level of like, what are we actually talking about? We're talking about the exams, right? And then figuring out how many students are seeing those exams. So there's a variable number of course sections, a variable number of unique instructors, a variable number of unique exams coded, right? Sometimes faculty would use the exact same exam in year 1 and year 3, and we didn't, if they were literally the entire exact same exam, then we wouldn't code that exam a second time. So one of the things we did in terms of, so how do we get to that 4,020 number? Oh, here it is, look at that. Okay, so obviously, you know, we coded things as either individual questions or clusters of questions. So that clusters being like those multi-part things, right? Like use this diagram to answer the next 6 questions. Okay, well, you know, if you're teaching 400 students and you want to ask them about sort of a larger idea, you might break that up, you know, to facilitate grading or whatever. And so we tried to give, you know, the exam authors basically the benefit of the doubt by saying like, we're going to consider that all one question. Right, and we're going to give, like, say there's a 6-part question or 6 multiple choice questions that rely on one diagram or something. Then we would say we're going to consider that a single cluster and we're going to code it all together. So we're going to consider that holistically, essentially to give everybody the benefit of the doubt, recognizing like the constraints of working at a giant university. If we had the same particular question used, like a single question showed up different times on multiple exams, and those questions got coded multiple times just because reasons. We can talk about more if you care about that. One of the first things we did was, like Melanie was saying, you know, we used some of these kind of traditional measures of showing what happened. So essentially, do no harm kind of approach. So one of the things we looked at was mean final course grade. And DFW rate, or D grade, F grade, and withdrawal rates all put together for a given course. So for Chem 1 and Chem 2, that's the orange data. Oops. Oh. Okay. So you can see project year along the x-axis, and you can see the DFW rate, which is the triangles, decreasing pretty dramatically. and the mean final grade also increasing, still with a big spread, but increasing rather dramatically for a course that is looking at somewhere between 3,000 and 4,000 students every year. Like, this is a really meaningful change in the gateway sequence, in the gateway series for like a huge portion of MSU students. So so snaps to all the chemists in the room who really facilitated this. So students had significantly higher final grades in year 3 than year 0, and this practically translates, like right now, there's about 750 students, 750 additional students who will get a 2.0 grade or above in one of these courses than they would have 5 years ago. That's like, I just got the chills actually. Kind of crazy. So what happened in terms of the exams? Actually, I probably should have showed this slide first, but what happened in terms of the exams in chemistry, again, this is just particular to chemistry. So each data point here is an exam, right? And the size represents the number of students who are taking that exam. So chemistry has common exams, all right? And so all, whatever, X hundred students are taking the same exam, and so their bubbles are very large. Bio, it's different. I'll show you a slide with the bio data and the physics data soon. You'll see that it kind of varies depending on the discipline. So there was sort of a wholesale change in chemistry, right? They were shifting curricula. They were completely shifting curricula. That didn't quite happen in bio. This is sort of unique to chemistry in the project. But we did see this increase for chemistry. There's our chemistry data again, just a little bit smaller. Here's our bio 1 course here. It's bio 161. All right, so year 0, we see, again, so you're going to see more bubbles for bio 1 because there's no common exams. So you see in year 0, we didn't really see any questions that sort of would help us elicit this evidence of three-dimensional learning. And then there was some movement to varying degrees in different sections, depending on, maybe some of the instructors were fellows, maybe some of them weren't, but they were toying around with changing their exams or doing something different anyway. So that's what the bio 1 data look like. Bio 2 looks pretty relatively flat overall. And I think there's good reason for this. Bio 2 has had a lot of activity occurring around it and in it from some dedicated faculty who have been really working on incorporating models, arguments, and data and collaboration into the course since like 2008 or 2009. So it wasn't that surprising to see them already have kind of a spread at year 0. And you can see there's a little bit of movement maybe towards year 3, but no statistically significant differences between 3 and 0. And then physics looks like this. So physics is sort of flatlining a little bit. Physics has these kind of little glimmery sections up here in years 2 and 3, which were also new curricula kind of experimental pilot sections that actually now, as far as I know, are kind of getting some more traction and seem to be moving. They seem to be moving more students into sections like that in this year and in the coming years. So that's it. We have a whole this data and a whole bunch of accompanying data just got accepted into Science Advances, so you can see it soon. I'm definitely not checking for the proofs every day at all. Waiting for them, but. There's more underneath this. There's more. This is the tip of the iceberg, and there's more. If you're interested in more, we can discuss. So I think that's the last. Yeah. So now we're on to the video.
Do we want to discuss assessment first and then do the video?
I think maybe we should keep going.
Let's keep going. We've got some questions at the end.
Yeah.
So, like Becky said, the assessment protocol has been developed and utilized in many different ways. The observation protocol has taken a little bit longer to get off the ground, so that is my primary role here. And so, again, this protocol has a similar purpose to look at this change over time that's been occurring here and soon elsewhere at other institutions. But it also has a secondary role, which would be to help faculty improve their instruction. And so we're kind of in the thick of trying to figure out what are the features and criteria that should be included in this observation protocol, and I can kind of show you some of what that looks like at a more detailed level. But you may be first wondering why we're making up our own protocol. So when looking in the literature at other protocols, many of these other protocols are looking at the how and the who of what's happening in classrooms. They're looking at the instructors and the students and the interactions, talking about active learning and things like that. But not many of them are looking at information about what is being taught. And that's really what we want to think about, is the content, what the content is, and how it's being used, and how it's related to other courses and other disciplines. And so the initial development did look at many of the hows and the whos, as well as the whats, and it looked somewhat like this, and I'll show you a larger version in a second. But if you look up here, it's kind of hard to see. So there's lots of little blue boxes, and those are trying to just kind of show when a clicker question happened, or when there was some kind of specific interaction, or if there was lecturing going on. And it's more of a timeline piece, but at the bottom, the purple and the red are trying to kind of get at, is there a phenomenon being discussed? Are there core ideas, science practices, those sorts of things being discussed? And that is where we're really wanting to focus, and we've kind of moved to mostly just considering that portion, and I'll show you what the new version of that looks like in a second. But if you look at the top of this, it looks like a very active classroom. There's a lot happening. It's not all lecture. There's lots of questions, different things being elicited from students. And so if you had something like a COPUS or some other observation protocol, this would look very impressive. But if we are looking at maybe the core ideas, those red boxes at the bottom, there's really nothing happening. There's not many instances or any instances of science practices or cross-cutting concepts. And so that's the direction we've moved, because that's what we're hearing about. So what we've done in our current iteration of this observation protocol is to first take the videos and try to figure out what our unit of coding will be. In many of these other protocols, they think about things maybe every 2 minutes or every 5 minutes or some sort of number interval. And that wasn't really working for what we were trying to do, seeing as many of these things kind of have some sort of like build up to whatever you're trying to do in your classroom. And those weren't really allowing us to capture kind of a build up to engaging in a science practice or a core idea. And so we moved in a direction to creating what we call chunks, or segments or sections of a class period. And we've done that now for all of our videos, but we've tried to kind of think about the videos in terms of chunks that center around a specific topic, not necessarily a core idea or a practice, but something that could stand alone as its own unit. You could maybe stop there for the day as an instructor and pick up the next day, and they're related by content always. So this would be an example of a timeline for a class period. And if you look at the start, this gray box over here, that's just the first 5 minutes of class that often appears to be what we call an administrative chunk, where you're just talking about things that have happened or are about to happen and just kind of getting your class on the same page. But these other chunks are chunked by content, like we said. And so the first couple are specific homework review things, where they're centering on some things that happened in the homework and kind of debriefing on those things. And then we have a dilution of solutions. We have a big activity here, and then another activity that are somewhat related but discrete. So they were pulled apart. So as you can tell, this was a chemistry classroom. We're talking about dilutions of solutions, exothermic dissolutions, endothermic dissolutions. So practically, how are we coding this? This is kind of just the first step in what we're doing. We're trying to think about the 3 dimensions, as we've said before. And we're starting first to think about, are there science practices being demonstrated? Those seem to be the easiest to spot, and so we've moved them to the forefront. They're also really important for doing what we want students to be able to do, which is to practically use their knowledge. And so we're starting first by coding for that.
Quick question.
Yes.
So science practices demonstrated or engaged in, or both?
Both.
Okay.
So that's exactly kind of what we've got here. So here's just one of the science practices, developing and using models. So thinking about the instruction as presenting an event or a phenomena, and that could be for the instructors or the students or both to be engaging in. And that kind of instructor or student aspect appears in pretty much all of these criteria. So if we've got some sort of phenomena, then they're asked to either construct or use a given representation, and then to go on beyond that and provide reasoning that links the representation to their explanation or prediction. So these would be the criteria for that specific practice, and we have criteria for other practices in a similar manner. We're also coding for instructor versus student. So we did say we don't really want to be categorizing all of the different things that are happening in terms of how the class is being conducted, but we do want to know who is doing that engagement. Is it the instructors, is it the students, or is it some kind of blend in the middle? And we're still kind of trying to define what all those different categories mean. So that's not the primary purpose of what I'm talking about right now, but that is something we're trying to tend to, because that is a really important piece. And then moving on to thinking about whether or not there's a core idea present, and then a cross-cutting concept. So for example, if we have the same timeline for this chemistry class I presented, this was the coding that came out of it. So it's a little overwhelming, but this first row here is science practices. So pretty much most of the class period was engaged in a science practice. 4 of the 5 content chunks had practices. Some of them seem to have more than one practice, which is debatable among the group, but there is or is not a practice. And then 3 of those 4 went on to also have core ideas in those chunks and cross-cutting concepts as well. Again, the specific core ideas may be many in number, or we may be debating them, but there is at least some kind of core idea present, and that's mostly what we're worried about at this point. So if I zoom in on that really long chunk right in the middle, I said that that was an exothermic dissolution activity. So what was happening in the classroom? So I've got a few screenshots to kind of help guide you along what happened and what led to the coding that you see here on the left. So in the classroom, calcium carbonate was actually put into baggies, like sandwich bags, as well as some water. And TAs walked around and actually let students feel what was happening while the dissolution was occurring in this bag. And so students were able to actually kind of feel and somewhat engage with that, the macroscopic portions of that phenomenon. And then they were asked to think about this dissolution and draw a picture of the calcium chloride solid as they conceived of it in the solid state. And so then they were given time to do that. TAs and instructors were walking around, helping them think about this and scaffold some of that. And then they were brought back together as a whole class to kind of debrief, discuss, elicit some of the student responses, and kind of come to a classroom consensus. Then they were asked to do the same thing, but now think about drawing a picture of calcium chloride as it is in the aqueous solution. And so then they did that in their small groups, or with their TAs and their instructors walking around, and then they debriefed again as a large group. And so if we go back to our developing and using models criteria, they did have a specific observation or phenomena that they were trying to explain or make a prediction about, but here is more explaining. They were then asked to construct representations of what that looked like before and after the dissolution. And they were asked to actually, in their large group debriefing sessions, provide reasoning that linked that representations with their explanations of what they saw happening. So we've been doing this for a while. We have actually successfully chunked all of these videos that we have, which is over 180 of them, and we're collecting more. But we're in the process of now trying to demonstrate some fidelity in the coding across our large team. If you remember our title slide, there's many of us So we're trying to kind of calibrate one another to coding the same way, and then scaling that up so that we can do similar things as we did with the assessment protocol. Try to see if we're making changes in the classrooms in the same way that many of the assessments have made change over the past 5 years or so. As well as then use it as a professional development tool with our STEM fellows as well. And some ongoing research questions that are beyond the scope of this talk is thinking about how are the faculty applying this framework in their courses, but also how are those barriers to adaption addressed. And so we're doing some faculty interviews, thinking about things from that perspective, because the different disciplines seem to uptake these changes differently, what's going on there. So that's a whole different side project. And then thinking about how are the outcomes for students. We talked briefly about some of that, and we've been collecting that data, but that's something we also need to dive further into. But we do have some discussion questions for the group, since this is a research in progress talk. So thinking about things from the respect that we are at a very large institution. So what are appropriate concessions to make with respect to three-dimensional learning when you're going from groups of 30 to like 400? Also, do students have to participate in practices to later be able to engage in them on assessments? That's something we've been talking about a lot lately. And then, what are essential features of the framework that you want your fellow colleagues to know and use? Was there a fourth question?
It was, but apparently it never got saved on top drive. So the fourth question was, about the core ideas. As you move forward through the curriculum, how explicit does the connection back to the core ideas have to become, particularly when the content becomes more complex and the connection back to the core idea becomes often more diffuse. So that was another question. But anyway. Do you want to show me?
I will show the next slide, because we do have a very large team, so it's not just the three of us. So there are many of us here at Michigan State. There are some at Grand Valley State, Kansas State, Florida International, as well as some previous group members, such as Joe and Sarah. So, I will go back to the questions.
Can I ask a different question?
Sure.
I was just wondering what's happening in the other institutions then. If that's something, just briefly, like
The other institutions.
where things are headed with other institutions, or
So the idea is that the other institutions, there's at every other institution, there's someone who's been a member of the primary team here, who's leading the work of the other institutions. So they are also participating in the fellowship program. They're also participating in the fellowship program. And we just had our first meeting last week, actually. So we had all 4 institutions and with teleconferencing. But the idea is that can they replicate and see the same, or are they able to do it better? Do they see the same kind of movement if they engage their faculty in the same way? And here we're attempting to, well, complete transformation, but also to move out to courses.
It's a different question also, if that's okay. I had a question about some of the assessment findings, and I want to say thank you. It's really interesting talk. I thought it was really interesting that you're making these assessments potentially much more complicated than the prior assessments, and yet at the same time it also seems like there's a lot more scaffolding within them. So, you know, as opposed to just having that one quick question, you're also kind of leading students through a process of thinking about it. And I was trying to think about the related findings of a lot more students not having Ds or dropping out and having higher grade point averages. And I was wondering if you thought that even though you're making these assessments potentially much more complicated, if the scaffolding is making it that students are doing better, or the instruction is changing and that's why? I mean, that's what you would hope. But like, so how do how do you account for making assessment so much harder and yet grades going up so dramatically?
That has to be you as having taught.
So I think the results in chemistry, which were not typical of everything else, we gave you the best case scenario there, are because of a confluence of events. So one thing that we didn't mention was that the chemistry, when chemistry transformed the way it did, Amy Pollock, who's the director of general chemistry, took over and ran with this program. But what we also had was an NSF-sponsored curriculum that was put into place and then adapted for this huge numbers of students. So we have a new curriculum, we have different assessments, we have a team of dedicated faculty and really good communication among the faculty. So it was the the best of all case scenarios. So I think it's a mixture of all those things. Yeah. So yeah, that's what I think. But I don't know.
So I have a question that's actually related to your second question. So your second question, I suppose you're trying to get from us, is students need to participate in scientific practices in order to be able to succeed on the assessments, right? I would argue yes. But that brings me to my question. And I can give you my reasons why I would argue yes too, but I actually want you guys to answer my question too. I get at the high school level, right, particularly from chemists and physics teachers that, oh yeah, this is all really lovely, but it takes a lot more time, and I have content I have to cover. So while this sounds really good, I have to really prepare my kids for the test, so I can't do this. Now, I would imagine that faculty would even be much more stronger in that response. So instead of engaging their kids in practices, they're going to want to cover content. How do you deal with that? What is that, Melanie?
So you're exactly right, of course. You have to remove content. And so that was part of the initial discussions right at the beginning of this, that we should have more. But the idea was that if we engaged faculty in thinking about what are the ideas that run through the discipline, and then think about some of the phenomena that we discuss, and think about how complex it is, particularly in chemistry. I think it's particularly problematic because there's a huge amount of understanding that has to be backfilled to understand any kind of phenomenon at the molecular level. And so yeah, so I think that is a huge issue, and I think that's why we've only seen, we saw such dramatic progress in chemistry, and we didn't see as much progress in the other disciplines. One of the issues is that it's hard to discard content. You're absolutely right.
So I'll go back to answer your question. So the argument, at least from my understanding, which I would argue, three-dimensional learning is that you really can't learn complex content unless you really engage in practices. And you really can't learn in practices unless you really engage in the content as you're trying to make sense of a phenomena. So we really want kids to succeed in more three-dimensional learning assessments. Then what they do, what they experience, has to be similar, right? It has to be three-dimensional as well. So that's my reason for giving you the response I did. So if all the faculty are constructing three-dimensional assessments, but they're not moving in the direction of three-dimensional teaching in their classroom, that's what I'm trying to.
Well, we don't know. We have a lot of video of people. We just haven't analyzed it all yet. But I think this is a pragmatic question, and it goes to this business that Kinsey was talking about. When we code what's going on, is the instructor doing all the work, or is the work equal? Are the students doing most of the work? And how do you handle that in situations where you don't have the opportunity to engage 450 students in 50 minutes to do what you might do in a high school classroom. So that's the nature of our question is, pragmatically, you know, if we want to do this, how far are we willing to go to let go of the ideal situation, I guess?
So, I hate it when people ask long questions, but I have one. It's sort of a follow-up to Joe's question, in the sense that, you know, what's the nature of the resistance to having students participate in science practices? And one of the things that seems to me to be a big dividing line between K-12 and post-secondary research and development has to do with the role of students' prior knowledge. Where at the post-secondary, in the K-12 level, is sort of taken as a given. And this comes out in the learning progressions in the framework, for example. It's taken as a given that students' prior knowledge has an important place in both assessment and instruction. At the deeper level, the question of whether you should design assessments that deliberately elicit students' non-canonical ideas and tries to analyze them seems to me to be very controversial. And even more in the instruction level, I can imagine the people saying, okay, so you have these, you know, people, that you have all the students expressing their misconceptions about what happens when CaCl2 dissolves in water. And when you do that, you are simply enabling them to reinforce their incorrect knowledge. And so you're doing worse than wasting time in the classroom. You are actually encouraging this incorrect kind of, and there's no place for that in a college class. And I'm noticing that prior knowledge does not seem to have a particularly explicit place in the frameworks which you're developing. And so I'm wondering about that.
So I will say that in chemistry, we assume almost no prior knowledge, sadly. And I think you're giving people who haven't thought about it too much credit when you talk about this business of giving concept inventories, right? Giving concept inventories or eliciting prior knowledge that is wrong. I don't think people have even think about that, except in physics. Because I can only talk about how it's played out in chemistry. And it's played out in chemistry in that we don't use concept inventories. I know, ever, as far as well, very rarely. And we are trying to build, but we start way back because a lot of what students bring with them from high school chemistry is not very useful. So, rules and things like that are not meaningful. So I'm not really answering your question very well because we don't. There's a divide between chemistry and physics about what we think about how we go about thinking about how to bring students forward. I think in the traditional, not traditional, but in a typical physics classroom, they will ask these questions. They will elicit the misconceptions, and then they will teach over the top of them, right? So they'll. Here you go. Yeah. Our goal here is, with these ideas, is to help, weave them together into something more productive. And I think we're able to do that because we have a team of people who are on the same page. Now, as we move forward, we find that I believe it's going to get harder and harder to move forward in that way. No,
So
that's not
can I
answering your
build
question.
on what
Yes,
you're both saying?
please, yes.
Yeah, and if I said non-canonical practice rather than prior knowledge, maybe I could word it differently. I would say in your work, you paid very close attention to the nature of students' non-canonical practices and how they can be transformed. And that's what I was trying to get at, not concept inventory.
Okay.
Right, yeah, so I was saying you do that implicitly all the time in the teaching by building in these practices. I think what
Right.
Andy was saying is resistance to doing that to building
Oh, I
in
see.
practices might be based on a fear of dealing with non-canonical ideas.
So-
Right?
So, yeah,
To
so,
some
so
degree.
actually the students have that fear. So, when we do that in the classroom, when we say, okay, here's something, write down what you know about it. And Amy will back me up on this, I know. You'll walk around and some of them they won't write things down. And when we interviewed them, so Olivia did some interviews on this, and the students said, I don't want to write it down because if I'm wrong, it will be in my head wrong. And I only want to write down the right things. And so I would say it's a bigger battle with the students than with the faculty. So, yeah.
But if you're getting this kind of response of, do I actually have to engage my students in practices if I have them on the assessment, that makes me wonder what.
No, I guess we put these questions up because we have this discussion among ourselves. Are we allowed to say that we're engaging in practices in a 450 seater auditorium where there's a discussion, but it's mainly being led by the instructor because it has to be for the most part? Does that count in your book? I think that's what we're asking. And we're really interested because we've had many discussions about this. And
So I would argue it's a whole lot better than not. Right, so if you said that to a class of 400 kids, how might I construct a model to explain such and such a phenomena? And you said, okay, take a minute and start sketching something out. And you said, well, let's see, what should we start out? What are some of the important components? What are the, then what, to identify some of your relationships? I think that would go a lot farther than just an instructor that goes up there and just draws something really quickly.
Right.
Right? So I think it's essential if you're gonna get them to be able to do that kind of stuff on their own.
They're not really doing their stuff on their own at that point, right?
Yeah, they are, Bob, right? If you give them a minute to like, think on their own. Now, maybe some kids are gonna decide not to think on their own, but they're not gonna think on their own anyways, right? So if you say to them, take a minute and write down, sketch something here, and then the instructor does that part, and then you say, let's go to the next part. You can even say, take a minute and share it with the person next to you. I mean, that's an engaging activity. Those little things are much better than just having someone stand up there and talk for 50 minutes straight and put information.
Right, I think we're all agreed on that, but I think this is coming back to when we code what's going on in the classroom. How do we code that? What do we say about that? Because we're interested in how does this transformation disseminate? And so there are many classrooms, and we've got many videos that we know, we've looked at them, they're very interactive, but there's no three-dimensional learning going on in there.
But it depends on what, so that's why I started off with my comment. What kind of model would you draw? What model would you draw, right? So it's not just saying, give me what model would you draw to explain this phenomena? It wasn't, what is your understanding of enthalpy? Take a minute and share it with your neighbor, right? That having a kid explain, having students take a minute and think about what their model, draw a model for how they might explain some phenomena is very different than saying, you know, discuss with your partner or think in your head how you might explain some kind of scientific concept. I would argue. Because the emphasis on is using your knowledge to explain a phenomena rather than just giving out an idea. One is fact or knowledge based, the other one is actually making use of your knowledge. And I think in large lecture halls, I bet you we would see a difference. You know, it's much better than just someone.
We do. I think we do.
I think that's what the whole course is about.
But
I have a question for Becky though, and it's related to what we just said. So you never used the word assessment on your phenomena when you were discussing your lab,
Oh,
right? You mentioned disciplinary core ideas, cross-cutting concepts, and practices, but you never said what they were in service. You never mentioned anything about how you try to structure assessments to focus on explaining phenomena.
so one of the, so each of the practices are sort of written in the 3D lab as like a set of criteria. So like Kinsey showed the one, or is like a correlate for the one for models. And they all start, all of the ones for practices start with there's an event, like some kind of event or observation or phenomenon. So that it sort of shows up like within, like enmeshed with the practices in the 3D lab. So we had them separate for a while, but we weren't finding a lot of, as I recall, I don't know, it's been a while, but I feel like we weren't finding a lot of places where we found a practice but no phenomenon. And so it was
so
sort
we
of like,
made it part of the criteria
right.
for practice, to say if there was one.
That's what I recall.
Yeah, I think that's how it played out.
I would like to, so the last question is one that I had, and I kind of just wanted to clarify. So when I was thinking about this question, like what are the essential features of the framing that you would want your fellow colleagues, not in science ed, not anywhere in this building, somebody who's doesn't know where this building is, right? Somebody who's over in BPS, right on the 5th floor, like what do you, I don't know, what would you hope that that person who is going to see, you know, umpteen million students in their career, what would you hope that they would know about the framework? That's one question that I hoped this group would indulge me in. It kind of like takes us a little off topic, but there's some reasons.
I think the work that you're doing is exactly what I would hope. I mean, the idea of like focusing on knowledge and use with the three-dimensional aspects and really focusing on both assessment and engaging in practice, I think, are super critical. I'm wondering about like faculty and others, whether they can use these for their own practice. So one thing our colleague here in the College of Ed, Ural Shah, does around equity is he's developed a tool, a video tool, that enables teachers to be able to video record their own classrooms and code whether, you know, which students are asking what questions of, how long they get to talk, those kinds of things. And I was wondering, I mean, it would be nice, it would be less threatening, perhaps, to have a tool like that you're using to assess one's own practice. Like, how much of my time am I really spending doing skill-based work compared to actually asking about phenomena, compared to, right?
Right. I think that's what we hope the 3D lab can be, but it's so, it would be so cumbersome for a person to use right now. It's like kind of untenable, right? To do something sort of as easy as what Neural would be doing.
Right, but I think the 3D lab, the assessment protocol, has found a lot of use. There's a lot of people out there already using it. We only published it last year.
I can imagine using it in K-12 settings.
Yeah.
So actually, so Kinsey mentioned one of our ongoing research questions is like, what are levers and barriers that what are levers and barriers that faculty go like, oh, that's really hard, or like, oh, that's easy, or you know, whatever. So one of the ways that I had an interest in audio recording our fellows meetings and then sort of, you know, reading them with a lens for levers and barriers. And one of the levers that has come out, or things promoting kind of integration of practices, or the three dimensions, is faculty going, oh, well, I coded my own exam with a 3D lab and it made me think like this, right? So it's not really a tool to get them to even necessarily change one of those particular questions, but it's like this thing that helps them shift their mindset a little. So that was kind of cool. There's lots of barriers too, so some levers.
I guess one thing too, sorry, go ahead.
I was gonna say for the observation protocol, I was partly just wondering, what would your ideal be in that? Like, what is the transforms? Is that they have, because I was thinking around these chunks, and it's like, if the classroom's chunked out more, what does that mean? Is that more likely or less likely that they would have 3 dimensions? Or, you know, what sort of changes are you looking for? And maybe you're still thinking about these things, I don't know. With the videos, and like, what, is it that every single chunk has all 3 dimensions, or is it something or some other characteristics around what's in the chunk?
So I don't think we're trying to advocate because every portion of a class has to be 3-dimensional. Maybe we are, but I don't think so. I mean, again, we kind of have to foster some skills like balancing equations and things like that to be able to engage in some of these other things. In terms of the chunking, we've kind of had, I don't know, different opinions on how that plays out and what it means if chunks are larger and smaller and how many there are and things like that. And I think moving towards these chunks has helped us because it's given us larger amounts of time to code, which then allows kind of the build up to some of these practices. So the fact that they're actually getting larger and there are less chunks within a class period for coding has meant that we're able to maybe capture some of the engagement and practices that we weren't capturing before.
So when you're looking at a change between, say, an instructor, and I don't know if you're looking for change or if it was, I guess I missed maybe with that, the sort of, what is it that you're looking for to measure in the end?
So right now, we just want to be able to say whether or not we can detect 3-dimensional learning in teaching. And then I think the plan is to move forward and detect change from maybe like year 0 to year 3, just like we did with the assessment protocol. But more so just right now, like, can we detect it or not, kind of the proof of concept type thing.
And maybe getting at the first question was also, I was just thinking of someone who's doing Bio 2 stuff and has his students go out outside of class to engage in like collecting data. And so I was wondering if that was a piece that might play a role, if, you know, if you're in these much larger classes, but maybe they have these small projects that they're working outside of class. How, if at all, would that tie into kind of assessing change?
So we talked about that to some degree, not necessarily in that specific context, but also like engaging in homework where they're then bringing those things into the classroom and talking about them or evaluating them, or even like lab. Students are often engaging in lab while they're not as specifically tied to the course. And so we've decided to not code for things like that unless they're explicitly using it somehow in the classroom, but then even then we're only coding what's happening in the classroom that we can observe because it's too hard to know what happened outside of that. So it's more so how are they using it in the classroom in that 50 or 80-minute setting or whatever. Yeah.
So I'm intrigued by a couple of things there. Right? This last one sort of suggests to me you need a 3D SAP for a syllabus assessment kind of program.
We floated that actually.
Right, where you follow just a small set of students to see what their level of engagement is in out-of-class activities, right, if you could, or something like that. Anyway, that was just thrown out there. Just add it to the mix. Melanie needs more things to do. My additional question, though, is several times now, and in the 3D lab kind of map that you all gave in the summer study, the observation protocols, you've said that, well, it's also important to teach skills, right? Meaning kinds of, and so my question is, have we blown it? Right? Is the framework missing a component, and this really needs to be 4-dimensional?
Jill's reaction is.
And the 4th dimension is there are some core skills, right, that need to be developed that scientists engage in, right, that are necessary and kind of part of the learning, right? So that those areas that come up all white, right, in your little 3D lab thing, are really measuring something that's important and that the scientific community thinks is important, and you just missed it in the framework.
You mean discipline specific or independent, context independent things that scientists must do?
If I were to guess, I would say discipline specific. Right, so you know, they were talking about skills in stoichiometry and balancing equations in chemistry, right? We can imagine things like vectors and that kind of mathematical understanding of independent axes in physics or something, right? That's a skill that is necessary to interpret phenomena that we're not measuring. Because if it keeps coming up all the time in everything, right, and that our faculty are doing what we're doing in classrooms, isn't that real?
Well, so I know in chemistry, we did generate skills, and they're, I don't know if they made it into the final paper. I think they did. Yeah, that's what I thought.
They are there.
They are there. So for chemistry, because I mean, like drawing structures, you know? You can't draw structures, you can't predict the properties of them. So, and in our work, we haven't seen, you know, consistently exams that have over 50% of points from three-dimensional, that have, from questions that have the potential to elicit three-dimensional. We have to be very careful to say that. I mean, nobody's, you know.
So in other words, the balance is really heavily on the skills as it is, so.
That's right. It's too heavily on the skills as it is,
Right.
but it isn't.
I don't think you have to stress it at
It's
all.
only on the skills, right? But if you don't have the skills, then you can't do all the other things, so.
I think the position of the framework is there's no such thing as skills.
Yeah.
That practices recognize that, you know, skills are conceived of as these all-purpose algorithms that you can apply anytime, any place, no matter what. And those don't exist. That what people do is, you know, algorithms have a use, but they have a use within the context, within specific subject matter domains and in response to specific phenomena. And so, you know, the question is it useful for kids to practice this sort of skill practice that's divorced from phenomena,
Yes.
divorced from content domains?
Yeah.
And you can make an argument, yeah, you know, that you do this sort of stimulus response thing and people learn to memorize, and, well, maybe, but in the real world, nobody is ever going to ask you a stoichiometry question. Things are going to come up where you need stoichiometry algorithms to do it. But that's a practice, you know, it's in the real world. It's not the questions on the exam, which is, it's not, you know, it's a little piece of a practice that's divorced from the context that would make it meaningful.
Sure. So I certainly understand that argument, but at the same time, that doesn't have to be the nature. Right? When we're looking at phenomena in any of our disciplines, right, and we're asking students to engage in making predictions and doing those other things, we're asking them to apply skills, right, at some point that are specific to that.
That's the idea,
particular age.
learning the skills rotely, that's what Andy said.
Yeah.
It's
Right.
avoid,
But we
so
don't-
if
but
I
when
was
we're
to
doing-
answer Becky,
Wait, Joe.
let me finish my point, you interrupted me.
Okay. So we don't ask people to do arguments divorced from phenomena. We don't ask people to do any of the cross-cutting concepts divorced from phenomena. So we consider a dimension to be something that is engaged with holistically when looking at a phenomena. So why should we consider skills to be divorced from a
Depends
phenomena?
what your kind of skill. If your kind of skill, engaging kids and being able to figure out how much of something is formed when something reacts together, I would argue that that boils down to engaging kids in mathematical thinking around the conservation of math. It's not rotely teaching them how to balance a chemical equation separate from the chemical equation and not understanding what they're doing. Most kids, when they look at a chemical equation, this is so well documented, right? Do not understand that the chemical equation represents a real world phenomenon. To them, it's not any separate than doing the crazy stoichiometry problem. It's just an isolated skill that they have to know, right? So it doesn't make, it's your argument, is just, it's different from the theoretical premises of what the framework is built upon, which Andy, I thought, articulated really nicely, is this one that you can't separate things from practice.
But we could do the same things with argumentation, right? We could say, let's do all the forms of argumentation,
What are you
right?
talking about?
And teach argumentation divorced from these other things, right? And we would have the same objection, right? So.
And no one would come up being a good arguer.
'Cause
Or
then-
they come up becoming what
Are you
we,
both arguing the same thing?
We are, yes. So
I was
think we
hoping-
have extra time for
I was
discussions
hoping
here.
to build on one other thing that's that's perpendicular to this, which is the idea that Melanie brought up of these, trying to code these highly interactive classrooms or interactions that don't necessarily meet the qualifications of 3D learning. And actually, that is something that I'm more interested in figuring out how you can add to this coding, because I think the interactions and the relationships between the instructors and the students with the students, so that they can take risks about their ideas and trying.
So we already have coded that.
Okay.
There are lots of protocols
Yeah, yeah.
in higher ed for
Yeah, yeah.
coding classrooms and doing those things, and we've already coded them all. We've got all 180 videos coded for what kinds of interactions are going on in there.
Like the quality or just the presence of?
Only the presence of.
Okay.
We haven't done, discourse
Okay.
analysis.
Yeah,
on
sure,
some
but I
of
just-
the videos, but yeah, so,
Do you see any correlational effects of?
We haven't really looked yet.
we haven't got the other part
That's
of the
protocol.
protocol.
Okay.
But we have got, we certainly have instances of videos that we have that are highly interactive, done by highly competent people who, but when we code and when we look at them, they're doing rote things. They're doing rote calculations, right? It's in physics, as you might imagine. There's no phenomenon, no consequence of the calculation, nothing. But it's highly interactive. So,
I guess I mean something different by interactive.
yeah, I know. But all the literature in higher ed, if you look, there's a paper in Science that was published not too long ago, and Marilyn Stain, who's coming here to give a seminar. But all of the protocols that are used are just, are they talking, are they not talking? Who is talking, are they not talking?
There was a proposal in some paper, or there was a paper on, I can't remember if it was a paper published or not published, but they were trying to basically just measure the noise level of a classroom.
That's right, they
Oh,
used
yeah.
the noise, no,
There's
it
a
was,
decibel
it was in PNAS.
It was?
Yes,
You used
the noise level.
Right,
They
like
said the
noisy
noise
classroom
level
equals, you're
was
talking equals good. I mean,
Can you believe that?
If you go to a lot of urban classrooms, those kids would score really
It was
high.
the proceedings of the National Academy of Sciences. So there, so.
Andy could maybe talk about this point. This was published actually in Taking Science to School. And there's this goes back to Bob's question. So there's in the chapter on learning, there's some really interesting statements that when you take classrooms that just engage kids in activity, right, basically show no learning any differently than classrooms in which there's lecture. And that's why Taking Science to School really pushed engaging kids in meaning-making and sense-making activities like building models and explanations. And that's the difference, right? So there's lots of literature that really supports that just activity, i.e. doing skills, isn't any better than just taking part in pure lecture. That the literature is really clear on that. And that's why from 2008, when we did that published, until the framework and the next generation of science standards, we've had a big push on trying to have meaning-making practices, not activities, meaning-making practices, like engaging kids in model building, argument, explanation, around making sense of phenomena. You want to answer that, or you're in that?
Very oftentimes, for an assessment item, the LAP isn't done, the LAP is, when you're 3D lapping something, if it doesn't get a 3D mark, it's because it's lacking reasoning. So if you look at the 3D lap in the supplemental, the reasoning, you're going through this criteria, the reasoning component is there for almost every single practice. And if it doesn't have that, that's immediately what makes it not have that. So exactly what you're saying, the LAP is taking that into account, but how do you do that for the LAP?
Yeah, so I was thinking of something similar, Joe, with response to Becky's question. And in some ways it's an orthogonal take on the essential features of the framework. And so, that I think you've sort of taken the 3 dimensions and put that at the top and say underneath that there is meaning making and phenomenon. And so they're not apparent at the top level, but they're apparent underneath. And I think some of us might be inclined to sort of go the other direction, say the top level is, it needs to be about phenomena, and students need to have a voice as they are engaged in developing models or in trying to figure out explanations and things like that. So how do you make sure that those things, the student voice or student meaning making and phenomena, are really apparent in the lab?
And so.
Lap or the lap?
So I'm gonna come, I totally agree with you, and yet, as, I'm teaching organic chemistry right now, and it gets, as you move through the curriculum, it gets harder and harder to consistently connect everything that you're talking about to phenomena and to core ideas, because the distance that you're moving away, well, in organic chemistry, it's all about forces, right? Force, positive attracts negative. You got that, you got all of organic chemistry. But you know, the things that I am required to teach, because my students are going into somebody else's class next semester, they're a long way from reality, I guess. A long way from, I mean, everything is taking place in a highly symbolic realm at an invisible and also invisible. And I'm kind of struggling with that, and I would be really interested to have feedback on that. You want to pardon?
And this is true in physics as well, right? We're constantly dealing with very significant abstractions, right, that are not even readily lab accessible. And particularly if you look at like a quantum 1 class or something like that, right, you're really kind of at that level.
We're not talking quantum 1, we're talking like freshman software.
That's quantum.
That's
Is it
quantum.
quantum?
So in chemistry, we introduce quantum and spectroscopy. So spectroscopy is evidence for quantized energy levels. So you can do it that way, but I'm struggling a bit with
I think,
although they're doing a lot better.
yeah. Underlying critique is not so much that all teaching has to be explicitly connected with phenomena. The underlying critique is that we are teaching science divorced from phenomena to students who have no way to connect it back. And so what I want to be assured of if I were teaching organic chemistry is as we go into more abstract realms, we are not just leaving students behind for whom this abstract realm is totally meaningless because they have no
and that's exactly
tools for
what
connecting back
happens.
to phenomena.
So when we interview students, you know, they can, you know, the reason why it has such a fearsome reputation is because they have to memorize everything. And there's so much stuff to memorize. And because they don't have those underpinnings that faculty assume that they do.
Yeah.
Anyways, it's 1:28,
Okay.
so we did go our extra half an hour.
Thank you.
So I really want to thank
Discussion, isn't it?
Becky and Kinsey and Melanie for leading us off. And maybe this is a start of the kind of conversations we'll have throughout all these research talks in progress. And hopefully we'll get more people to sort of partake and ask questions and really debate. And I would love to follow up on your question with that. Maybe others can join us as well. So,
Yeah.
because I love organic chemistry because I thought it was so phenomena-based.
Okay.
Wow, where did you take it?
Anyways, so a little card for you guys to share.
Thank you.
And then we have a little crate presents. Here we go.
Oh, it's the other side.
You can share the card along the other one. Actually, three cards.
Thank you.
Oh, I love these.
Yeah, there you go. And it's got a little crate symbol on it too. See?
Wow,
Sick.
you guys are high tech.
Thank you.
Thank those guys back there.
Very
Can we-
much. That's excellent.
Thank you so much.
Yeah, welcome. Thank you, guys.
Thank you.